Most people don't know this, but a single U.S. aircraft carrier holds more aircraft than the air forces of most nations. With that much capability, you can imagine how powerful aircraft carriers are. Among the 11 aircraft carriers owned by the U.S., the USS Gerald Ford is the newest and largest, representing the most advanced and formidable naval vessel in the world, with the ability to project immense firepower through its fleet of aircraft. The Ford is a symbol of American military might and a crucial asset when diplomacy fails. However, despite its cutting-edge design and vast capabilities, the USS Ford has been facing a lot of technical issues that have hindered its full operational potential. These issues have affected the carrier so much that other smaller and older aircraft carriers are performing better than it. But why would the Navy spend billions of dollars only to end up with a faulty aircraft carrier? And most importantly, what are they doing to fix these problems? At the heart of any aircraft carrier's combat power is its ability to conduct cyclic flight operations, the continuous process of launching, recovering, rearming, and refueling its embarked aircraft. This capability is crucial for sustaining naval air campaigns over extended periods, enabling months-long operations without the need for resupply. With a fully trained and equipped crew, a carrier can maintain round-the-clock flight operations, projecting air power thousands of miles from its position on the open seas. The sheer magnitude of weaponry and strike capacity that a carrier air wing can deliver is virtually unparalleled. Facilitating this vital cyclic operations process are three critical systems: the weapons elevators, catapults, and arresting gears. Deep within the ship's interior lies an area known as the bomb farm, where bombs and missiles are carefully assembled just prior to use. This minimizes risks associated with storing armed munitions on board. Once prepared, these weapons are carried to the flight deck via the ship's network of weapons elevators. After aircraft are armed, refueled, and prepared on the flight deck, they rely on the carrier's catapult system to provide the powerful acceleration required for launch, since no modern fighter can generate enough thrust for an unassisted takeoff from the constrained deck space. Traditionally, these catapult systems have harnessed the power of steam generated from the ship's nuclear reactors, building up tremendous energy that is then released into a controlled burst to shoot aircraft off the deck and into the air. At the opposite end of the cycle, an aircraft's recovery relies on the carrier's arresting gear, a system of heavy cables stretched across the angled deck. As the incoming plane's tailhook engages one of these cables, a complex series of hydraulic engines and pulleys work to rapidly decelerate the aircraft from its landing speed to a full stop in a short distance. This integrated three-part system of weapons transport, launch, and recovery has formed the core of U.S. Navy carrier operations since World War II. The legacy systems that have served the Navy well for generations were showing their age and limitations. Time was a crucial factor. The electro-hydraulic weapons elevators could be painfully slow, while each aircraft recovery required manually resetting the arresting gear parameters for that specific aircraft type. These painstaking processes constrain the speed of cyclic operations. Moreover, the intense forces involved with the steam catapult launch placed tremendous stress on the airframes. With each launch, aircraft experienced a massive, near instantaneous jolt of acceleration rather than a smooth, gradual increase in speed. This punishing force inevitably took a toll on the structural integrity of the planes over years of repeated use. Also, since every aircraft has a different weight, precisely calibrating the catapult for each launch became more an art than an exact science. These constraints had very real cost in terms of increased maintenance requirements and shortened airframe lifespans. The Navy recognized that optimizing and modernizing the main cyclic operation systems was crucial. Faster, smoother, more efficient launch and recovery cycles could yield significant benefits. Higher operational tempo, reduced fatigue and wear on airframes, and substantial long-term cost savings through decreased sustainment demands. This drove the push to radically overhaul these systems for the new Ford class of carriers. The goal? was to develop technologies that could provide tailored, low-stress launches and recoveries while accelerating the total cycle time. To meet these ambitious goals, the USS Gerald Ford incorporated a suite of new technologies unlike anything previously seen on an aircraft carrier. The most important among these is the Electromagnetic Aircraft Launch System, EMALS, the world's first system replacing the traditional steam catapults. Rather than harnessing the power of steam and hydraulics, EMALS relies on a burst of intense electromagnetic forces provided by alternating current flowing through a sequence of magnetic coils along the flight deck. This ingenious design confers several important advantages over legacy systems. First off, EMALS can automatically sense and adjust the precise weight and configuration of each aircraft preparing for launch. Using sophisticated software, it calculates the exact magnetic field strength required to impart the optimal acceleration force for that aircraft. This tailored application of force avoids overstressing the airframe while still providing enough launch energy. Additionally, instead of the aggressive standing start and instant shock force of a steam catapult, EMALS propels the aircraft with a smooth, gradual increase in acceleration, significantly reducing the structural fatigue on the plane, with far less plumbing, mechanicals, and support infrastructure compared to steam systems. EMALS also promises greatly reduced maintenance needs and cost of ownership over its lifetime. The USS Ford also revolutionized aircraft recovery capabilities with the Advanced Arresting Gear, AAG. Legacy systems relied on hydraulics that required manual adjustment for each trapped wire engagement. However, AAG uses innovative water twister technology to automatically calibrate arresting forces. Large steel discs spinning inside water-filled drums generate precise acceleration and deceleration forces that can be tuned in an instant based on the incoming aircraft's weight and speed. This allows a smoother, lower stress deceleration and automatic reconfiguration for the next recovery without human intervention. But EMALS and AAG are just two of the carrier's pioneering integrated technologies. The ship also boasts cutting-edge systems like dual-band radar, advanced computing networks, and comprehensive electronic warfare capabilities. These combined innovations promise to usher in a new era of enhanced capability and reduced workloads for sailors. However, as revolutionary as these new systems are on paper, bringing them to operational reality has proven an immense challenge with severe growing pains. While the potential benefits of EMALS and AAG were very promising, actualizing these new technologies has been plagued by substantial technical issues that have severely hindered the USS Ford's operational capabilities. A recent report from the Department of Defense's Operational Test and Evaluation Division shed light on the myriad of problems continually impacting these critical systems. For EMALS, hardware reliability has been a major problem. The positioning block sensors within the electromagnetic rail system have experienced frequent failures, with the ship's crew having to replace all of them on multiple occasions just to keep flight operations running. Design flaws have also hampered EMALS' performance and maintainability. Initially, there were no centralized diagnostic capability, forcing technicians into the laborious process of manually tracing faults locally along the extensive system until the manufacturer could develop and install remote monitoring tools. Even with these software patches, troubleshooting and repairing EMALS is still a difficult task that requires extensive training and technical documentation. The Advanced Arresting Gear has fared a little better in terms of reliable operations. Despite hardware upgrades and software updates to these three AAG engines installed on the Ford, the report states that there have been little improvement in the system's uptime and overall availability to support mission needs. The reasons cited include persistent glitches, failures during critical arresting operations, and challenges in executing repairs. Compounding AAG's problems is the Navy's baffling decision to not install the planned fourth arresting gear engine engine on the Ford, at least initially. Having just 3 engines instead of the intended 4 severely limits redundancy and the capability to sustain continuous cyclic operations if one of the systems goes down. While the potential payoffs were enticing, the Navy now faces the harsh reality that these systems were pushed to the ship before they had achieved the necessary design, maturity, and reliability. However, the report did highlight one positive note regarding the USS Gerald Ford's recent operational employment. During the ship's inaugural 8-month deployment in 2023, the crew successfully conducted 9,266 arrested landings, nearly equaling the total for the previous 5 years combined. This suggests that despite the technical problems, the crew is gradually mastering procedures to maintain an acceptable operational pace under the current constraints. Even at that, realizing the USS Ford's full multi-billion-dollar design capabilities will require the U.S. Navy and contractors to go back to the drawing board. If you enjoyed this video, make sure to hit that like button and subscribe to this channel for more amazing videos.